about the labs a little bit, not really too much. Next week, we'll talk about more formal lab reports, but I'm going to talk about the two things I want you to do sometime this week by next Thursday. So if you go to modules in the lab handouts, there are a bunch of documents I put on there, a bunch of crazy documents, but they're all really short and they're all stuff, if you've ever taken a lab, you've seen before. Accuracy and precision, error categories, expressing error, sig figs. The one thing I will say is sig figs are important, but you probably all know how to do them. If you don't, we'll talk about them when necessary. And if I see people that are putting millions of digits, we'll talk about it. But I'm pretty sure you all know these four, and I'm not going to go over those. For those of you who have never made a graph in Excel, and I know that there's other things, other programs like Google has Sheets or whatever that is. You can make graphs in other programs, but they have to have what's called an R-squared value, okay? Yeah, the rules for sig figs basically use the least amount. So if I'm multiplying 0.2 times 1.1, right, I would get 0.22. But because 0.1 really only has one sig fig, I would put that as 0.2. And if you're adding numbers, you keep the least amount. It's really simple. And you're not going to get docked for, I'm not going to be checking your sig figs unless someone does something crazy like gives me 15 digits on an answer. Obviously, you don't want to do that. But the simple rule is use the least amount. Where you're going to get a lot of practice with that is really probably Wiley Plus. Wiley Plus might tell you that you need certain sig figs on answers. I think everyone knows sig figs though. You guys get it pounded into you over and over in all your classes. The simplest rule is whether you're dividing, multiplying, adding, or subtracting, keep the least amount of sig figs that you have in your smallest answer, because that's how well you know it, okay? So this document is how to make graphs in Excel. For those of you who have never done an Excel graph, just make sure you go through and read it. It's for the new Excel, unfortunately. So you might have an older Excel that it's a little different, but this will take you through, and I'll let you do it on your own, how to make a graph and what it means. The one thing that I need to stress right now about graphs though, is if we say an X versus Y graph, that would actually mean that X is on the vertical axis and Y would be on the horizontal. So whatever comes first is the Y axis. So this, we're going to make a couple for pressure versus temperature graphs, but you need to know that pressure or whichever variable comes first is always the Y axis when you graph it, okay? Just be sure you're clear on that. Later on, we'll go through when we start using graphs, probably when we get to free fall, which is lab 4, we'll really do some stuff with that graph. Until then, I just want you to be able to make them. When you make a graph, it has to have a title. It has to have the axis is labeled with units, okay? Think about this as if you wrote a scientific paper and you included a graph, you better include the units and what you're graphing, right? Number 2, you never connect dots. These are discrete data points. They shouldn't be connected ever. Number 3, and this is a little weird, but we'll talk about this more during free fall, we never go through 0. The reason why is the y-intercept, where it intercepts this axis, that's a measure of your error based on your experiment, okay? That's systematic error, error that's inherent in either the ruler or the mechanisms you're using. And so you need to know what that is. That actually tells you how good your data actually is. And then you put a trend line. And in this one, we're going to be doing a quadratic and a cubic trend line. I'll go over that later. But we're basically going to make 4 graphs, 1 quad, 1 cubic. If you don't know what that means, quadratic goes to the power of 2, cubic goes to the power of 3 for 2 different data sets. And once you go through that, it's all pretty simple and easy. And then what I'm going to want you to do in this is I'm going to want you to copy the graph out of Excel and then paste it into a Word doc. And you can do it one of two ways. You can paste it in landscape mode, full page, or you can paste two graphs on the same page, but they need to fill the page, okay? I don't want like a quarter of a page, a little tiny graph on there. I want either half a page or a full page for each graph. Okay, that's good enough. And then we go through this module. So that's just to help anybody that doesn't understand Excel graphing. Hopefully it's really useful if you don't understand. You can always text me and say, hey, I'm having trouble with this. Can you take me through it? And I'll try. I don't know Google Sheets that well. I use Excel, but I'm certainly open to trying to figure it out for you if you're having trouble. This is a lab report cover sheet. And you're going to see on here that it says researcher, analyst, principal, investigator. Now I need to talk to you guys about something. I do labs a little differently than other faculty, okay? The thing is, I expect you guys to organize your labs. If you're in a group, organize the work however you see fit. However, the problem can happen when, let's say, I'm just going to use the top three students, Kevin, Ahmed, and Alexis. Let's say they're a group, and Kevin says, I'll get the data and do the data table. And Ahmed says, I'll do the calculations. And Alexis says, I'll do the questions and the conclusion. Great. But then you go to turn it in, and let's say one of them does a horrible job on their part, and they get a bad score. Well, two things happen. Number one, if you don't have a 90 on a lab, I will give the lab back to you and tell you what's wrong with it and let you fix it. Okay, if it's over 90, it's fine. Don't worry about it. But if it's like a 70 because someone didn't include the table of results, I'm going to say, hey, there's no table of results here. It's a 70 right now unless you get that table of results to me, okay? And I'll make sure that that's cool. Number two, if you're struggling with part of it and you need a little bit of an extension, I'm okay with that too. I don't like grading labs. I shouldn't say that, but I really don't. They take so much time to make sure that I see everything and that I catch any errors you guys have. So they're always quite a lengthy bit of work to grade. But I'm willing to give you a little bit extra time if you need it, if something's wrong and you don't understand what's happening. But number three is if you're in a lab group and something's going to be turned in with your name on it, you better see it before it gets turned in. So if you come and tell me, well, I shouldn't have gotten a bad grade because so-and-so did bad on it, well, you should have looked at it and checked up on it, right? It's not really an issue because I'll go back and say, hey, fix it. But just know that if you were in a lab, if you were a grad student, if you were working at a company, anything that gets turned in with your name on it, you better make sure you know it's solid. And I want you guys to make sure of that. Check each other's work. Be comfortable if someone says, hey, the table of results is a mess. I'm going to fix it, and go, okay, yeah, sorry, I messed that up. Okay. We've all got to learn. But the overall skills that you're going to get out of lab is you're going to learn a little bit about data collection, how to analyze that data and get meaningful results, and then present those meaningful results in a conclusion. And there's usually some questions to answer. The important thing for me is that you develop those skills. Some of you already have them. Some of you have already done chemistry and you're great. Some of you don't. And I want to help those of you that don't so that you're prepared for 4B and 4C and that you have really, really nice lab reports. Something I'm going to ask you to do once we start taking data is to keep a little notebook and turn in a page of where you collected your data. The reason for that, and I'm sorry, my dog is drinking water. The reason for that is we've been told by like the UCs that, at least a year ago we were told this, that we do kind of a bad job with our lab notebooks. So I kind of want to make sure you guys get in the habit of keeping lab notebooks. Number two, as a researcher, you never know when someone is going to do something stupid. I would have data being collected and someone unplugged something, power goes out, whatever, and you lose that data. The best thing you can do is keep a handwritten copy of what you're doing. I used to go through and I would have a computer collecting my data, but every few minutes I would jot down whatever my potential meter said so that I had a handwritten record in case a file got lost or destroyed. So it's really important once we get to free fall that you guys start writing in a small notebook. I don't care what kind of notebook, but it needs to be bound, writing down your data. Do it together if you're doing it in groups, but write down your data and keep a handwritten record that can't be lost, okay? Now, groups. I don't care if you guys do groups of 1 up to groups of 3. If 2 of you want to work together, that's great. If 1 of you wants to work on their own, that's fine. But no more than 3, please. 3 is about the right number to each kind of take a chunk and get it knocked out, and then not having too much work on the labs. However, if you do groups of 3 or groups of 2, switch up every once in a while who does what. We're here to learn, and while you may not want to do calculations, it would probably be a good thing for you to do the calculations once or twice, because if you get to 4B or 4C and you have to do calculations, you're going to need to know what to do. But I'm not going to micromanage that. That's up to you guys. I will say this. There is a Discord, I think, that someone made, and there's also our chat during class. If you want to join a lab group and you don't know anyone in here, be brave. Throw your name out there. Say, hey, I would like to be in a lab, and see who contacts you, okay? Exchange emails or get on that Discord. I don't remember who made it, but one of the other students in here made a Discord for you guys. So get together on that. As long as there's no more than 3 people on each lab report, you're great. Okay. So each lab report should have this page at the front of it. I just want to know who's on there. You don't actually, I don't care who did research, analyst, principal investigator. I just want your names on here. So each lab should have one of those. And if it's just you, just your name on it. And then for today, this is a data table of the data I want you to use. There's 2 different trials, trial 1 and trial 2. It gives you the pressure, it gives you the temperatures. And then there's these tables. So when you do your data table, you just write down your data right here on here. This is from the trend line that you'll make for each graph. So for trial number 1, you'll do it with a quadratic trend line. You'll write down the quadratic, linear, and constant coefficients off that trend line. For trial 2, the 3rd graph, you'll do the same. That's pretty easy. But they're there for you. Feel free to pull them right out of there and put them in your lab report. Your lab report should be like a Word document that has data tables. We'll go through it, but data tables, table of results, calculations, questions answered in full, complete sentences, double-spaced, and a conclusion. Also, here's the table of results for you. I will, in general, every lab give you these to help you with calculations. There's no, oh, there are the table of results. So here's the table of results. Again, take it right out of here, copy and paste it into yours and fill in the blanks. These are the only calculations that we're doing on this one. I want to talk about these really fast. These are all percent differences. So if you have a theoretical value, you can do something called percent error, but we don't have a theoretical value. We're going to have 2 distinct numbers, and it might be a little weird to compare them. And yeah, I don't know if we can really compare them, but imagine I want to compare 2 students' test scores. Student A gets a 60, student B gets an 80. And I want to know the percent difference between those 2 values. What I do is I go 60 minus 80, which is minus 20, over 60 plus 80, which is 140 divided by half, which is 70. So I'd have minus 20 over 70. I take the absolute value of that, negative 2/7, and I multiply it by 100%, and I report it as a percentage. And that tells me how different they are over the weighted average of the 2 of them. You just add all the values together and divide by 2. That's only useful if you do not have a theoretical value to go on, okay? So let's say you were comparing the temperature yesterday to the temperature today and you wanted to know the percent difference, right? That's what you would do. However, if you were trying to find gravity in the room and you came up with 9.4 and you wanted to compare that to 9.81, 9.81 is a theoretical value. And we'll talk about that next time. But for now, you just need to do these for the different coefficients. It's pretty easy. So let's go to the actual lab handout. There's a little bit here about labs, graphs. Make sure you just read it real fast. A linear slope is this. We're actually going to talk about that during free fall, not right now. So that's not that important. But starting on this page, it gives you the procedure. I would really like all your lab reports to start with a purpose statement. I'm not really going to mark you off if it doesn't have one, but it should kind of introduce, hey, this is our lab. We were doing, pressure versus temperature graphs for non-ideal gases, something like that. We made 4 graphs to understand how to make Excel graphs. It can be super simple, but please make it complete sentences, double space it, make it look nice. The first graph is the first trial's data table. Go into Excel, graph P versus T, put a quadratic trend line. Now, I cannot say this enough because invariably someone doesn't do this and they get counted off. When you display that trend line, put it on the graph with the R² value. If you don't know, whenever you put a trend line, there's 2 different things that sometimes show up depending on what program you're using. R² is a measure of how well the graph sits, or your data sits on the actual line, the actual trend line that you make. If it sits right on it, it has a value of 1. This is super important. An accurate trend line is really above 0.99, not 0.98, 0.99. It needs to be basically 1. And if it's less than about 0.99, it's not very accurate. You have outliers, and that's okay. Something I should back up and say, this is not chemistry. And I know in chemistry, a lot of times you guys will be told, oh, you need to get within 5% or 3% of the mass or the number of molecules or whatever for the experiment you're doing. I don't want you to worry about how close your data is, how good your data is. What I want you to worry about is why it's not good. So if you do something and you get 140% error, I want you to report it. And I want you to tell me why you think you got that error. The reason being that I don't want you to ever start lying about data. I don't personally like the idea that you're being graded on how good your numbers are, because that encourages you to fudge numbers. And in real experiments, anyone who's ever done a physics or chem lab, you know that sometimes experiments just go bad. You're having a bad day, you stayed up late, you just didn't measure something correctly, or something unforeseen happened. You cooked it too long, whatever. But I want you to get in the habit of just reporting your numbers. And if they're bad, say they're bad. They're bad. Maybe at a later date redo the experiment, but it's not chemistry. I need to know why the numbers are bad, but I don't need them to be good, if that makes sense. And it's far more important to me that you learn why errors happen, why you have errors. That being said, you need to assume that you guys are all perfect researchers in this class. I don't want to know about the human error. I don't want to hear that, well, I didn't measure something with my ruler correctly. That shouldn't happen. Imagine you're at a job and they ask you why your numbers are kind of cruddy. And you say, oh, because I don't know how to measure. Yeah, you would be fired, right? So we're going to assume that that didn't happen, even though it very well may have, and that's okay. What I want to know, though, when you talk about errors, error within the experiment or within the environment, meaning if we do free fall, you'll have error from air resistance. But if we're doing like sliding down a plane and we're assuming that it's sliding down without friction, well, there's friction in the plane. There's friction in the experiment. And we'll always talk about that before we do the experiment or at some point. So just remember, your error can be bad, but I need you to tell me why. And we'll get to that. So for trial 1, you're going to make a graph with a quadratic to the power of 2 trend line. The other thing is, if you're doing Google Sheets or some other graphing programs, sometimes you'll see RMSE. And RMSE is root mean squared error. It actually goes backwards. If you think about error, so the amount of error is how far your data points lie off your trend line. You square that error and you add it all together. So that's where you get the root mean squared error. So you divide it by the mean, and that tells you how much error total you have in your experiment versus your trend line. You really want that to be a 0. The weird thing about RMSE is that because it's dependent on the values of your data, it has to be weighted correctly. And sometimes people don't weight it correctly. And you'll see an RMSE of like 60,000. That's really bad. But it might actually just be a weighting error because they should have divided that by 60,000 and they would have gotten like a 1. In general, RMSE you want really, really, really small. It's the amount of, you can think of it as the amount of error in the entire experiment. R squared value you want very close to 1. You can think of it as how exact the data matches the trend line, and if you were to divide it in a certain way, would you get basically 1 if they were identical, okay? So R squared needs to be close to 1, RMSE needs to be 0, just remember that. The third and fourth trial will be that second data set, or the third and fourth graphs. And you'll do the same thing, a quadratic and a cubic for those. So you'll have 4 graphs. Each graph will have a title, axis with units, a trend line, and an R squared value line, okay? And then you'll print them 2 pages, 2 graphs per page, okay? And then make sure you fill out the data table from your trend lines, and then do this data analysis. So this is just showing the percent differences on the variant graphs coefficients. And you fill out the table of results with those. So your lab report will have a purpose statement. It will have 4 graphs. It will have a data table with all your coefficients from your trend lines. It will have the calculations of the percent differences. It'll have a table of results. And then we have a couple questions. This one I've talked about a whole bunch, but it's R squared, and how accurate is R squared, and how accurate are your R squared values. And this is just one of those fun, hey, list all the things that they did wrong. Now, we have discrete data points. We never connect discrete data points. So that's wrong. There's no title. There's no units. There's no axes. There's no trend line. There's no R squared value. I mean, on and on and on. So just go through and tell me what they did wrong. For both of these, complete sentences, double space. They don't have to be elaborate. They can be short to the point, but I really want you to answer them in complete, thoughtful sentences, okay? And then lastly, you're gonna write a conclusion. A normal conclusion, we would do these things like what you found, the error and uncertainty in your experiment as actual numbers, causes of error, and how to get a better experiment. We'll talk about that next time. There's no real conclusion here. What I want you to do is just compare your graphs, tell me things you noticed, tell me things you found. Your percent differences are probably going to be a little bit off each other. Why is that? And here's a big hint, since you're all here. They're totally different trials. Would you expect them to be perfectly the same? I mean, I made up that data, but if you were doing 2 different gases, why would their coefficients even be the same? Probably they wouldn't. So this is really just an introduction, a real soft introduction. Graphs are super valuable, and we'll talk about why. Probably Tuesday we'll talk about things. As a preview of that, I just want to say, and you guys might not agree with me right now, but eventually I think you will. We as humans are not very smart. We're clever and we're ingenious, but we generally need things done easily so that we can understand them. And Graphs are a very good way for people to understand data. They're a visual way, and most of us can look at something and understand it better than we could understand just numbers. If I gave you an Excel file of numbers, you might not get anything out of it. But when I graph it, you see the relationships and you understand them. When we do vectors on Tuesday, vectors are very elegant math, but they're also visual, and they help because they're visual. You can draw things. You can show what's happening with the motion with vectors. And that's why vectors exist. There's an elegant mathematical formula and structure to them, which we'll talk about. For Tuesday, I want you to go through chapter 3. It's all about vectors. And we'll talk about vectors, and we'll have an actual homework assignment with points on vectors. And we'll have a lab on vectors, which I'll try not to make too horrible. But we need to understand how to use vectors mathematically and visually. And that's what we're going to do next week. And then we'll have a quick lab next week on measurement and error. And error is kind of difficult. I don't want to get into it today. So any questions on this? You can do it in groups of 3. You can do it in groups of 1. I don't think it'll take you more than half an hour to do. Someone might have been doing it right now and almost be done with it. So the other thing, normally a lab report's worth 100 points. This one's only worth 50. It's pretty fast and easy because there's another one associated with lab 1, and that's this IOLab doc. If you do not have the IOLab yet, it's okay. You don't have to do this yet. But if you have your IOLab, I want you to go through this. If you click on these links, they will take you to Macmillan's website and explain how to download the drivers and get the IOLab installed on your computer or Mac, okay? You might need to download drivers. There's a video that takes you through it. It's a very short process, pretty easy, okay? There is one weird little thing. You may need to go in and right-click more info and give it permission for some weird reason. They talk about it in the video, but I had to do that on mine for it to work, and I'm on a Mac. And then you might want to create a shortcut. You can't see it, but I have I'll share it with you. Here's my desktop. I have a little IOLab shortcut down here because I use it a lot. And then once you do that, you'll have this up. If I click on this, there's a little red like USB drive you have to put in your computer. That's why you have to have a computer or Mac to do this. But when I click on this, eventually it will start, I hope. It's probably not on. The IOLab thing comes up. And if I were to plug in, I'm not going to do it right now. You can do it on your own. When you plug it in, it'll show you how to calibrate it with this, meaning the sensors might not be reading exactly 0. What we've found is you want to calibrate as much as possible. Sometimes the calibration gets messed up between experiments. And then the only thing you really need to do on this is try to get this lesson player working. It tells you how. There's a video that shows you how to do it. When you do it, it's going to tell you on like the 7th or 8th slide to make a graph. You're going to use a big spring on your IOLab and hook it on, and then you're just going to kind of put it flat and pull it around, and you get a nice graph of what the IOLab's doing. All I want you to do, this is the important part, screen grab or take a photo with your phone of that graph. You don't have to find the slope. You don't have to do anything. I just want to know that you got your IOLab working and you were able to collect data with it, okay? So that's all this lab you really have to do is get me that graph that shows that your IOLab is working and you're able to collect data. It'll go through a bunch of other stuff, but every time we use the IOLab, I will take you through how to do it, how to collect data, where to get the data from, all that good stuff. Sometimes I will even give you the data of my experiment in case yours doesn't work. I encourage all of you to do the IOLab data together and then use whoever's data comes out the best. I would really like that if you're working in a group of 3. Because sometimes some people's ILabs just don't work great. But it's up to you guys to go through this, get your ILab up and running. It really doesn't take long. Get me that screen grab that shows that you got it running of the force graph. And it really shouldn't take maybe 20 minutes. So together, if you're on it, this might take an hour or so to do it. Okay, but otherwise it's not hard. I just want you to play around with your ILab and get it up and running. I'm going to say one other thing. I've had a couple questions about the homework. Homework 1, 4C. For some odd reason, just remember that if you know what I'm talking about, then 4C, it asks you about this error that's like 10 to the minus 14 milliseconds. Well, it's in milliseconds, so go 10 to the minus 17. When you add error, if you took like 4 different rulers and added their lengths together, you would add the uncertainties. So it asks you for the uncertainty after 9 times 10 to the 6th times. Multiply your uncertainty by the number of times. And you should get something like 10 to the minus 11. For some weird reason, for one student, it wasn't taking the answer and it kept telling him it was wrong. So, but other than that, that's what you have to do today. You don't have to do anything today, to be honest with you. You could bail on this and work on your other stuff so that your weekend will be free. But I would really like by next week for you to have the ILab done. I know that some of you don't have it yet, so we'll push that. But the graphing lab needs to be done by next week. It's really not that much work, and you can do it together. So are there any questions for me that I can answer for you right now? I'm going to stick around. I want Emilio, if you're still here, I don't know where you went.
Yeah, I'm here.
Okay, I wanted to talk to you about some stuff, just about the course while we're here. Anyone else, if you don't have questions, feel free to bail out of here.
Professor, I have a question.
Yes, sir.
So for the labs, if we're in a group, do we each turn in our own lab, or do we turn in one lab for the group?
No, thank you so much for telling me that. If you're in a lab group with 3 people or 2 people, only one of you needs to turn in the lab report. But make sure that your names are on that cover sheet so that I know who did it together, okay? But yeah, only one of you. They'll be online. Do them in a Word document, and then when you're all done, it's probably fastest to do it as a PDF and just submit it. When you go into the assignment tab, yeah, and if someone can get that Discord link to Emilio, that would be great. If you go into the assignment tab, like see graphing, I can't do it because I'm the professor, but you should be able to submit a file right here. And so you just submit your PDF file or you submit your photo for the ILab. And by the way, Emilio, that is your guys' Discord. People are going to get together to do homework and stuff. If I catch anyone using it during the final or find out or someone rats somebody out, you will get disciplined for that, which means I will have to report that. So don't use it during exams. But as far as working together on homework, lab assignments, anything else, feel free. Use it. The best way to do physics is together. It's the best way to learn. So I'll be here for a little bit talking to Emilio about the class. And if anyone has questions, if you start on the lab, if not, again, you can always text me. And we can also talk about it on Tuesday when we get together. So before you leave, Tuesday, chapter 3, go into the e-textbook and look it up. One last thing I'm going to say is you may notice a change in our Canvas page. I'm going to try to set it up so that each chapter kind of has their own little submodule that you'll have the readings at one click this weekend. I don't know if I'm going to be able to do that, but I'm really going to try to make it easier for you guys to have the homework assignment, the quizzes, and the textbook readings all in one place without having to hunt for it. Okay, but otherwise, I hope everyone's safe and happy and healthy, and I'll talk to you all later. I'll be here talking to Emilio. Once everyone's gone, I'm going to bail. So if you have questions, make sure you stick around and ask. Otherwise,
Thanks, Professor.
You're welcome, guys.